Hi everybody, this is going to be our note for 5.1. We're looking at direct variation today. So we're going to be starting this kind of chapter and section with this investigation. We have this person Susan who can jog a steady pace of 150 meters per minute, and she does this for 6 minutes. So we're going to complete a table of values showing the distance that she jogs. So again, with our table of value, like we learned in our chapter 2 booklet, we're going to have some x and y values. Choose x here and y here. And we know this is going to happen for 6 minutes. So we can say that it's going to happen over 0, 1, 2, 3, 4, 5, and 6. So before we get around, let's maybe identify these variables before we continue with our table of values. So what are the two things we're measuring in this question? And one of them is going to be our independent variable, and one is going to be our dependent variable. So the first thing I can see is kind of minutes here. Minutes involving time. And like we talked about in our booklets, we said whenever we have time, majority of the time, it's going to be the independent variable. So we're going to say time, and we'll just include our units, which is in minutes. Our dependent variable would seem to be our kind of distance traveled, because your distance here, the 150 meters, depends on how much time has gone by. So our dependent variable will be distance measured in meters. So we can see that our time here, our x value, independent, again for the x-axis, is going up by ones and refers to our minutes here. And then y will refer to our distance. So at 0 minutes, how much distance has been traveled? Well, also 0. At 1 minute, well, we know she's traveling at 150 meters per minute. So at 1 minute, she's traveled 150 meters. After 2 minutes, 300. After 3 minutes, and we're just going up by 150 every time. Then we get to 600, then we get to 750, and then 900. So this makes sense because after every minute, she's been traveling 150 meters. So now we're going to graph this relationship. We're going to graph these points, and then we're going to draw a line of best fit. So when we make our graph, we're going to have our independent variable on the x-axis. So I'm just going to label this x, and the y-axis is going up and down here. So we already established that our independent variable is time, so I'm going to put that label down here. Time, again with the units in minutes. And then on our y-axis we were measuring distance in meters. So on the bottom here I'm just going to go up by every other line is going to be 1, 2, 3, 4, 5, 6, 7, 8. Now we kind of look at our lowest and our highest number, then we go a little bit higher in case maybe we want to do any extrapolation like we learned in that chapter 2 booklet. So I'm just going to draw my lines here. For the y-axis we'll go up by 100 every time. So I'll just put, I'll go up by every other line is 200, which means every line has to be 100. And I'm leaving this page this much space because otherwise it might be kind of crammed putting all these numbers in. So every other line is going to be 200. That's good. So now we'll be putting our points in. So if we point at 0, 0, then we point at 1 and then 150. Well, if this is 100 here, then 150 has to be in between them. For 2, it's going to be at 300. For 3, it would be 450. 4 would be 600. 5 would be 750, which would be here. And we already see the dots are forming a line. And 6 would be 900, which would be here. So it says use it, draw a line of best fit, so I'm kind of drawing this on the best fit. I'll even extend it a little bit further. And we put an arrow at the end to show that this line could go on longer, but we're just making it go up to here if we want to. So describe the shape of this graph. Well, we can see that it's going to be positive because it's going from left to right, it's going upwards. And with these points, we can kind of say this is a strong correlation because all the points are lined up. So it says, where does it intersect the vertical axis? So where does this line cross this y-axis here? Well, it seems to be crossing it right at 0, 0. So now we can write an equation to figure out the distance in meters that Susan jogs in t minutes. So we're going to use these as our variables, like they kind of defined for us. And these do match our independent and our dependent variables. So we can say the distance that Susan jogs is, well, 150 meters every t minutes. So like at 1 minute, it was 150 meters. 2 minutes is 300. So it seems like whatever the time is, or how many minutes has gone by, we just times that by 150, and we'll get the distance traveled. So we can say d is equal to 150 t. And then it says use the equation to determine the distance that Susan can jog in now 40 minutes. So now that we've figured that out, we don't have to like graph this further all the way to 40 minutes if we don't want to. So now we have an equation just to do calculations a little bit faster. So d is equal to 150t. D is equal to 150 times 40. And again, I don't like doing math horizontally like this. I would go normally downwards, but because I'm pressed for space, I'm just going to do it going from left to right. So 150 times 40 gives me a distance of 6,000 meters. So consider the distance Susan jogged in 2 minutes. What happens to the distance when the time is doubled? What happens to the distance when the time is tripled? So at 2 minutes, it's 300. If we double that, it goes to 600. And if we triple this, times it by 3, we get the distance has also been times by 3. So we can say down here, when time is doubled or tripled, the distance is as well. Which means if we change the time, if we double or triple it, the distance will also be doubled or tripled. So now we're going to look at another person, Trish, and Trish has a steady jogging pace of 175 meters per minute, also for 6 minutes. So now we're going to complete a table of values for Trish, and then we're going to graph the same information on the same graph. So I'm going to do the table here. Again, x is our time. And again, this happens for 6 minutes. So we're going to have, again, 0, 1, 2, 3, 4, 5, 6. And for our distances now, it's going up by 175. So at 0, we still have 0 though. After 0 minutes, no distance has been traveled. So then we have 175. And then if I times that by 2, if I double that, we'll be at 350. And then we'll be at 525, 700, 875, and 1050. So these are our points for Trish. And we're going to put these on the same graph just so we can compare the two lines and see if there's any similarities or differences. So if we can also label this, we can label this one for Susan. Another one will be for Trish. So we have one at 0, 0, again, and then at 1, 175, which, I mean, if 150 is here, 175 has got to be a little bit higher than that. And then at 2, we're at 350, which if this is 300, 350 would be there. Then at 3 be 525, which would be kind of here. 4 is at 700, which would be here. 5 would be at 875, so there. And then 6 would be at 1050, which would be like there. And then we can also see that this is also forming another line right here. And we should extend it a little bit further again, just in case we want to like extrapolate that data. So now we look at the next set of questions in regard to comparing these two lines together. So describe the difference between Susan and Trisha's graph. Well, what do you can see some similarities. I mean, they both are positive going up from left to right. So I should label those two for Trish. They both seem to be kind of going up by the same kind of like steady amount, like by 150 and by 175. But some differences between them. Well, we can see who's going faster, meaning who is always covering more distance than the other person. So I mean, if Susan is at 150 at 1 minute, we can already see that Trish is a little bit further at 175. And when we get to 6 minutes, 900 meters for Susan, and Trish has gone 1050. So we can always see that Trish is always going a little bit since she's going faster, always going a little bit further every time. I mean, at 1 minute, Trish had gone 25 meters over what Susan had, but now at 6 minutes, it's like 150 meters more. So we can say the difference is that Trish is moving faster and covering more distance. So let's put this graph here. We can put our answer here as well. That looks better. Okay, so we can say Trish is moving faster than Susan. She travels further. And how can we describe their graph specifically? Well, I'd say that Trisha's graph is a little bit steeper than Susan's. So like this, I'd say, is a steeper slope compared to Susan's slope. Slope meaning like, I don't know, if this was like a mountain or like a hill. And if this was the hill we had to climb versus like this, look, these are two different hills or mountains. Like this one is definitely steeper than this one. So we can say that Trisha's graph is steeper than Susan's. So now we can write an equation for Trisha's jog in t-minutes. So again, distance is going to be equal to, this time 175 meters times t-minutes. So again, if it's 1 minute, it's 175. 2 minutes would be 350, and so on. So now we can describe the difference between Susan's equation, which we said was d is equal to 150t, and Trisha's, which is d is equal to 175t. So as we're looking at differences, we can actually see that the equations are very similar. Like it has our dependent variable, d every time, equal to the number, the speed, sorry, times the number of time. But just so we saw Trisha's graph was a bit steeper, we notice that Trisha's equation also has a higher number there. So we can just say that Trisha's equation has a higher number than Susan's. Than Susan's equation, let's say. Which kind of leads to why she has a steeper graph, because we have a bigger number here. Let's just kind of a quick look at our investigation. We're going to be looking at different concepts with this again as we go on in this chapter. But one of the main things we can look at is how both of their graphs started at the very beginning. So this is actually an example of what we call direct variation. It is a relationship between distance and time. Well, for this example anyway. For example, Susan's table shows that distances traveled in various time periods at a rate of 150 meters per minute. When time is multiplied by a specific number, distance is also multiplied by the same number. Like we saw before, when the time was doubled, the distance was also doubled. Another way to describe this direct variation is to say that distance varies directly with time. So the graph of direct variation is a straight line that passes through the origin, and that's the big thing for direct variation. So we're going to be learning about a different type of variation in the next lesson, where they also go up by kind of the same rate and also multiply by the same number. But these graphs for direct variation always start through 0, 0. They have to pass through this origin to be considered direct variation. If it does not pass through the origin, then it's a different type of variation that we'll learn about tomorrow. So remember, direct variation goes up by a specific rate. We can say that's multiplied by the same number for like our dependent and independent variable, and it always passes through the origin. So let's look at some examples now. Sorry, before we get to an example, we have to look at one more thing called the constant of variation. So we saw with direct variation, it occurs when the dependent variable varies by the same factor as the independent variable. We saw that happening with the 150 and the 175, which was kind of the speed for both of those people. So what does this mean? In direct variation, the ratio of any two corresponding values, or those coordinate points, of the variables is constant. Meaning if we looked at our table of values, if I always kind of just divided the y value by the x value, the dependent divided by the independent, for all of these cases, whenever I divide these, I always get 150, which was Susan's speed here. And the same thing for Trish, where if I get her speed, which was 175, if I always divide the y value by the x value, we'll always get 175. So the ratio is constant. So therefore, direct variation can be defined algebraically as the y value, or the dependent variable, divided by the independent variable. And we're going to make that equal to m, which is our constant of variation. Or like, if we rearrange this though, like if I wanted to get rid of the fraction, we learned before that we can multiply both sides by the denominator. So to get rid of that fraction, we get just y is equal to mx. So I can kind of do that over here. Oops, x there is equal to m. I want to multiply both sides by x, so that cancels out the fraction. And I'm left with y is equal to x. So we call m the constant of variation. So again, it's just kind of our, in this case, Susan's speed was the constant of variation, and then Trish's speed was also the constant of variation. So in examples where distance is your dependent variable and time is your independent variable, the equations above can be written as distance over time is equal to m. And if I wanted to, again, just get rid of the fraction, distance is equal to m times t, where m is still called the constant of variation. So now let's get to an example. So it says the Frederick family travels 250 kilometers to a relative's home. The distance d in kilometers varies directly with time and hours. So find the equation relating d and t if d is equal to 43 when t is equal to 0.5. What does the constant of variation represent? So we can kind of use the equation we learned up here, or if I know my distance is equal to 43 and the time is equal to 0.5. We can kind of put our units if we want to as well, like we know this is going to be in kilometers, and that this will be in hours. So our constant of variation, d over t, again, kind of our order doesn't matter, like m is equal to d over t, m equals d over t, like these mean the same thing. So we just put in what we know, 43 over 0.5, and we're going to get 86 And then we can keep our units there as well, since the D was measuring kilometers and the T was in hours. We can say this is kilometers per kind of 1 hour, which is kind of like our unit rate actually that we talked about in our review. Or we can write it out kind of fancy, like 86 kilometers per hour. So that is our constant of variation. And if we're talking about something like 86 kilometers per hour, just like in our example with Susan and Trish, this is our this is the speed, or how fast they're traveling. So use the equation to determine how long it would take the Fredericks to reach their destination. So we're going to kind of look at our equation for a constant of variation, and this is actually what we did in chapter 4, where we're kind of changing these formulas so they're isolating for variables, for different variables, sorry. So like we have constant of variation here. If we want to solve for t right now, because we want to figure out the time, how long it will take, well, the longer way to do this is we're going to multiply both sides by the denominator to get rid of the denominator. So we have d is equal to m times t. And then I want to get the letter t by itself, so we'll divide both sides by m. So time is equal to the distance divided by the constant of variation, which just happens to be the speed this time. So our time is going to be equal to the distance, which is 250 kilometers, divided by the speed, which we said was 86 kilometers per hour. And when I divide these two, I'm going to get 2.9, and our units for time has been hours, so we're just going to put 2.9 hours. And that's how long it will take to reach the destination. Alright, in our next example it says about 1/3 of all water used in homes is for toilet flushes. The table shows the water use for a standard toilet manufactured in 1985. Why do we have this information? It doesn't matter, but let's just answer the question about it. So first we're going to graph this. So we have to figure out which is our dependent and which is our independent variable. Does the water use depend on how many times the toilet is flushed, or does the number of flushes depend on how much water use there is? So usually the water use depends on how many toilet flushes there are. So this will be our independent variable, which will be on the bottom here. And the water use depends on the number of flushes, so that'll be our y-axis. Also putting in the units, and we'll label this x and y. Now luckily we can see that both of our values are going up by the same amount here. That's kind of our definition of direct variation. So for our graph, we can put our scales on the x and y-axis to be kind of the same, but please don't think that we can just always put this as the scale and it just matches up like that, because it really just depends on the data. So if this was like a scatter plot, we'd have to choose a proper scale that goes up by the same amount. It just so happens it works out that these numbers go up by the same amount. So I'm just going to put these numbers up here, going up by, every other line is 65, so 65, 130, 195, 260, 325, 390, and then for toilet flushes we'll just go, every one is 5, 10, 15, 20, 25, 30. And again, it just so happens that these are going up by the same amount, so that's just going to be our scaling for this. And then as we put these in, we can see, well, these are definitely just going to make a straight line here. That, and then we can join our points with a line. So we just graph this. Is this direct variation? Explain. So we can say, yes, it is. So we can say, first off, where does it start from? It starts from the origin. And we also know this is going to be direct variation because, well, these go up proportionally. So like as this doubles, this also doubles. As the number of flushes triples, the water use also triples. So we can say that there is a constant of variation. Oops, constant of variation. Meaning it goes up by the same amount. But the main thing also is it starts from the origin, because we're going to learn in our next lesson that. But if it doesn't start at the origin, so to determine the constant of variation, what does this value represent? So it's always kind of the dependent variable divided by the independent variable. So if we picked any one of these, let's say, I don't know, 260, and divided it by 20, well, what are we going to get as our constant of variation? So we're going to get 13. And this is, I guess, liters per flush. Meaning every time they flush it, it's 13 liters of water being used. So write the equation to represent the water use with respect to flushes. So we can say water use, which is, well, we used y before, so water use is y, is equal to 13x. And we can kind of put these variables, I guess, so we can say let y represent the number of liters, kind of used, and let x represent the number of flushes. So we can check this. I mean, if we know for 5 flushes is going to be 65, so if I just got, 13 times 5, that does equal 65. And if I did it for 10, well, 13 times 10 is 130, which is what we get over here. So again, proportionally going up by the same amount every time, as always going, every flush is 13 liters. So if I wanted to find it for 17 flushes, which again we don't really have, because it seems to be between these two. And if I could do interpolation by looking at 17 flushes. So this is 17.5 here, so a little bit less than that, but sometimes it's hard to read on the graph. So that's why our equation is usually a little bit better if we get a more accurate answer. So 13 times 17 flushes, and I get 221 liters being used. So therefore, 221 liters of water is used. So that's it for our first lesson in Chapter 5. So just remember, direct variation starts at the origin and has a constant of variation. So I want to try the homework, and thanks for your time.